Complete breakdown of CHEM 1810 Lecture 2, Quantum Mechanics and Electron Waves. Ready to unlock the secrets behind electrons and quantum waves? Let's dive into CHEM 1810 Lecture 2 and explore atomic mysteries. In this lecture, you'll journey beyond simple particles to see electrons as waves. Sounds wild? It's the foundation of quantum mechanics. First up, in the hydrogen atom, you can't pinpoint exactly where the electron is. Instead, you map probabilities, how likely it is to be somewhere. Thanks to Heisenberg's uncertainty principle, the electron's position is fuzzy. You can only predict the chance of finding it within a certain range. Now imagine electrons acting like waves and particles at the same time. Yep, wave-particle duality is real and it's mind-blowing. Electrons show wave behavior like diffraction and interference, just like light does. This means they carry momentum and wavelength simultaneously. Let's talk de Broglie wavelengths. This formula links an electron's momentum to its wavelength, revealing its wave nature mathematically. Here's the magic formula. Wavelength equals Planck's constant divided by momentum. Smaller mass or higher speed means a shorter wavelength. For instance, an electron speeding at 1/3 the speed of light has a wavelength close to the size of an atom. Crazy, right? Next, diffraction and interference experiments prove electrons behave like waves, from Young's light experiment to Davison-Germer's electron diffraction. Davison and Germer's work was the first direct proof that electrons show matter-wave behavior, turning physics textbooks upside down. Diving deeper, the wave function, or psi, is a math function that describes an electron's wave motion, where it can be positive or negative, adding wave phases. The key is probability density. Psi squared tells you how likely an electron is at a given spot, painting a cloud of electron density. So, the wave function doesn't pinpoint electron location but gives a probability map. It's like forecasting weather, but with electrons. When wave functions combine, they interact through interference. Sometimes waves add up, constructive, sometimes they cancel out, destructive. Constructive interference boosts probability. Waves in sync make the electron's presence more likely in certain spots. On the flip side, destructive interference lowers the intensity. Waves out of phase can cancel out, making electron presence unlikely or zero. In the hydrogen atom's 1s orbital, these interference patterns form clear electron density shapes, revealing the secrets of chemical bonding. Here's a quick cheat sheet on must-know formulas. P equals psi squared for probability, and lambda equals Planck's constant over momentum for wavelength. Don't forget wave addition and subtraction formulas for interference. They tell you how psi waves combine to shape electron probabilities. The core takeaway? Electrons aren't just tiny balls, they're wave-like when confined, changing how we understand atoms and chemistry. Quantum mechanics flips classical physics on its head at tiny scales, explaining electron behavior through wave functions instead of fixed paths. Wave interference controls where electrons hang out around atoms, directly impacting chemical bonding and reactivity. It's the atomic dance floor. So the next time you think of electrons, imagine vibrant waves weaving a complex pattern, the essence of quantum mechanics at work. Want to master quantum mechanics? Keep exploring wave functions, experiment evidence, and how math reveals the unseen world of atoms. Thanks for joining this deep dive into CHEM 1810 Lecture 2, where particles meet waves and physics gets fascinating. If you found this helpful, hit like, subscribe, and share with friends who geek out over atoms and electrons. Let's keep unraveling the quantum universe together. See you in the next lecture breakdown.